Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, about 6 days ago. It introduces HumanX, a framework that compiles human videos into generalizable robot skills, achieving over 8 times higher generalization success compared to prior methods. The paper is titled HumanX Toward Agile and Generalizable Humanoid Interaction Skills from Human Videos. And as we'll see later, the implications for acquiring versatile, real-world skills without manual reward engineering are really promising. Figure 1 illustrates the complete HumanX pipeline. On the left, the process begins with single-view videos of humans performing various activities, ranging from sports to cargo handling. The XGeneral component then synthesizes this footage into physically plausible humanoid interaction data within a simulation environment. Finally, XMimic leverages this synthetic data to train robust policies, allowing the physical robot on the right to perform complex skills like basketball shooting and reactive boxing in the real world. So, Figure 1 gave us the big picture. Now, Figure 2 zooms in specifically on the XGeneral pipeline. On the left, the system converts raw human video into humanoid motion by retargeting the pose. It segments the action into contact phases, where the robot holds the object, and non-contact phases. For the contact moments shown in the top right, XGeneral anchors the object to the robot and optimizes the grasp for stability. Then, in the middle right, it uses physics simulation for non-contact trajectories, which supports augmentation by varying object types. Finally, the bottom right shows how Step 8 combines these into a seamless interaction trajectory. Well, with the data generation settled, Figure 5 outlines the training framework, XMimic. On the left, Stage 1 trains a teacher policy with privileged access to simulation data, ensuring it masters the task perfectly. In the middle, Stage 2 distills this knowledge into a student policy via behavior cloning. Because the real robot lacks privileged info, the student learns to act based only on realistic sensors. Finally, the real-world deployment section shows this student policy controlling the physical humanoid, executing skills at 100 Hz. Alright, moving from the training pipeline, Table 1 details the main simulation results. It compares the proposed framework against baselines like Skill Mimic and HDMI across 3 tasks: basketball catch and shot, badminton hitting, and cargo pickup. The columns track standard success rate as well as generalization success rate on unseen variations. Looking at the top rows, we see that prior methods struggle significantly with generalization, often scoring near 0%. In contrast, the bottom section shows that adding data augmentation and the teacher-student architecture improves these scores drastically, reaching over 90% for badminton. So, after verifying the method in simulation, Figure 10 demonstrates how these skills transfer to the physical world using motion capture for perception. The top row shows a sustained basketball catch and pass sequence, where the robot dynamically interacts with a human partner. Below that, the football kicking strip illustrates the humanoid approaching a ball and striking it with precision. Moving down, the cargo pickup panels show the robot handling bulky objects like water jugs. Finally, the bottom strip captures a reactive fighting scenario, proving the system can respond to human movements in real time. While the previous figure focused on interactive tasks using motion capture, Figure 9 showcases the robot's blind capabilities. Here, the robot performs diverse basketball skills, relying solely on proprioception, meaning it controls objects without external vision. The top row displays fundamental moves like a standard jump shot, continuous dribbling, and ball pickup. However, the bottom row demonstrates advanced agility with a complex pump-fake turnaround fadeaway shot on the left, followed by a dynamic layup on the right. Alright, having seen the qualitative demonstrations in the previous figures, Table 3 now provides the hard numbers for these real-world experiments. The left side lists interactive tasks relying on motion capture, where skills like cargo pickup and football kicking maintain success rates above 80% over 50 trials. Meanwhile, the right column details the blind NEP maneuvers, which rely solely on proprioception. Here, complex actions like the pump fake and spin move succeeded in 9 out of 10 attempts, validating the system's robustness. Wrapping up, 2 key takeaways stand out. HumanX demonstrates that humanoids can acquire agile skills directly from video without manual reward engineering, and it proves these policies transfer robustly to the real world. This suggests a scalable pathway for training generalist robots using massive video datasets. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.